Here we're going to look at 1995, question 4. Okay, part A. So, at a glance, it's actually quite a big, complex looking question. We have two particles, A and B, on a smooth pulley. And then we have this added twist. When after a second, it passes C and picks up another mass. Okay, we look down through what we need to answer. We have a whole set of 4 different things. Now, one of the little tips with these questions is to take them one step at a time. Part 1 may help you with part 2, or may help you with part 3, and so on, and we work our way through it. Sometimes the question can look like quite a complicated system, but it only gets complicated by the end of it. So let's work through this for the moment, and we're going to look at part 1 first. Okay, so just the initial acceleration. So in this case, we have our pulley, and we have our little particles either side, and they're starting at the same place. There is A and B. Okay, that's B, that's A. Now, we know our force on them. Get this little one in black. It's one string, so there's going to be a tension pulling up on each side. That's fine. And there's going to be a force going down on them. So we'll do all our forces in black here. Going down, B is 0.5 kilograms, so 0.5 G. And A is 0.4 G. Okay, now if we have a little look at this one and just take a small bit of common sense, B is heavier than A, so our whole system is going to be moving like this. All right. That just helps keep our signs conventions tidied up. Okay, so initial acceleration, well, this is going to be an F equals ma problem. So if we look at F equals ma, okay, because we have forces and we want acceleration. For A, we are going to get the force is going upwards, so T, slightly sad blue pen there, T in black, T minus 0.4 G equals the mass 0.4 with acceleration, which is A. And because they're on one string, there's a common acceleration between the two of them. All right, and we'll just do a small little rearrangement there, nice and tidy. T equals 0.4 A plus 0.4 G. All right, B. Well, B is going downwards, so 0.5 G minus T equals 0.5 A. Force, mass, acceleration. So we're going to sub in T, and put into B, so 0.5 G minus 0.4 A plus 0.4 G equals 0.5 A. Okay, so now just a little bit of housekeeping, tidy this up. I'm going to do this second step in one line because the only way you'll really make a mess of this one is you'll screw up this minus sign here. So 0.5 G minus 0.4 A minus 0.4 G is 0.5 A. All right, keep our G's on one side, our A's on the other side. So we are going to have 0.1 G on this side, and the minus 0.4 over is going to be minus 0.9 A. So A is 0.1 G over 0.9 G. Sorry, 0.9. Whoops, watch that stuff. And that basically ends up being G over 9. Okay, that's our initial acceleration. There we go. All right, so part 2. Now, so the velocity of A just before it picks up mass C. So again, this is kind of nice. We haven't brought C in yet. It's still our basic diagram that we have over here. All right, so what do we know at C? Well, at C, so just before C, we look back on our question, we will see that the time equals 1. Okay, so we want the velocity of A after 1 second. Well, V equals U plus AT. We want this. We know that was 0. We've just figured out the acceleration down here, and we have the time. So velocity is 0 plus G over 9 factor of multiplied by 1. All right, so the velocity is g over 9. It's not too bad. Now we just multiply that one out a little bit, so that of course is 9.8 over 9, and that equals 1.02 meters per second. Apologies, that equals 1.09 meters per second. All right, I'll leave these ones here because it might be easier to go back to this later on in the question. So now part 3. They're being very nice to us here because they've told us we need to use the principal conservation of momentum. Okay, velocity of A after it picks up mass C. Now, this is one where we need to be a little bit careful. What we have initially was a system where we have A going up over pulley and B was down here. All right, and we are interested in A and C being there. All right, so that's our whole system connected by a string. All right, the place where you can go wrong in this one is if you forget about B. B is still part of the system. It's like someone dragging along by a rope. It still matters. So, principal conservation of momentum, PCM, is basically the momentum before is the momentum after. Before equals momentum after. All right, so our momentum before, well, let's look at our 3 different particles. We have our initial speed. So we're going to call the initial speed before equals u, and then we just worked out that one there is, I'm going to call it g over 9. Okay, and speed after we want. So we have A plus B multiplied by u, because they're both going at that speed, plus C multiplied by 0 because it wasn't moving, and that equals A plus B plus C, all multiplied by the speed after, because they're all going to be moving together. All right, so let's put some numbers into this one. A and B are 0.4 plus 0.5 times g over 9. I'm now rather glad I've gone back to the fraction because I see that's going to be a 0.9, and that equals all of these guys together, 0.4 plus 0.5 plus C, we'll double check it now, is 0.2 by our unknown V. Okay, so 0.9 g all over 9 equals, add all these guys up, 1.1 V. All right, tidy that one up there, and that one is going to be 0.1 g equals 1.1 V. V equals 0.1 g over 1.1. We see we've got space for that here, so V equals g over 11. There we have it. Now we've got to go to a fresh page for our last little part of it. The distance of A from C at the first point of instantaneous rest. Now, this might be kind of one that confuses you when you first have a little look at it. So let's just think about our system for a little moment. We'll draw a diagram again. So we now have a system looking something like this. So B is still 0.5. And A and C together are 0.6, 0.4 plus 0.2. Okay, that's B. Now, applying a small bit of common sense, we'll realize it's going to want to move like this. Okay? But eventually, because at the moment A and C are still going upwards. Eventually. So it's moving upwards. End of the day, it's going to go down. It's going to go up, 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 stop, and fall back down all the way again. All right? That's our movement. Okay, so now we know it's going to kind of go up a little bit further, and we want to know what's this distance before it stops. So this becomes a little bit more manageable now. We have some U forces. So unfortunately, since our blue ran out, we're going to do our forces in red. So let's think about what our forces are here. a new value of t. Okay, and then 0.5g and 0.6g. Okay, so a little bit of an F equals ma question. Blue's going to get sad. So for a plus c, now we know it's eventually going to go down this way. Okay, so we'll say 0.6g minus t equals 0.6 with acceleration. Now just to note, these are different acceleration and different tension values than we had in the first part of the question. If we really want to be particular about it, we could be calling these T2s and A2s and all that. I'd worry that might get a tiny bit confusing, so I'm just kind of sticking with the simple terminology, but they are different values. All right. And for B, F equals ma, so we know it's going to go all the way upwards. So T minus 0.5g equals 0.5a. Okay, in this case t equals 0.5a plus 0.5g. Just as before, we sub in t. Alright, so we are going to sub t into this top one here, 0.6g minus, this t value comes down, 0.5a plus 0.5g equals, we're still finishing this equation, 0.6a. Alright, a little bit of housekeeping. I'll fit this one on the page, 0.6g. Okay, I'm going to have to come up here to tidy. So we are going to end up with 1.1g on this side. Ooh, I did look at that. Made a little mistake I talked about earlier on. Okay, so we're going to end up with 0.1g here. Bring this across 1.1a. Okay, so a equals 0.1g over 1.1. Acceleration equals g over 11. Okay, so now I have my acceleration value. We want to know the distance. We know at the top of it, v is going to be 0. So if we think this one, v equals 0 at the top, a equals g over 11, u is the value we worked out just on the previous page. Okay, we called it v at that time because that's what we're looking for, but it was the moment just at the speed of the system just as it picked up c. So that was g over 11. Oh, it's going to be tidy, isn't it? And we want s. Well, what equation comes to mind? V squared equals u squared plus 2as. All right, off we go. 0 equals g over 11 squared plus 2a g over 11 by s. Now, you can see a little problem emerging here because we have an issue with some signs. Okay, and sometimes in these questions you can apply a small bit of common sense and work out the signs. But strictly speaking, we are looking for a distance, and squeeze it in blue, how much further up it goes. So we're going to call it this positive and down negative. Okay, now if that means if we're overall our acceleration is going this way, strictly speaking a is minus g over 11. Okay, and this will be a minus in here. Now, like I said, in the end of the day, in these questions you can see any of the errors back and forth quite easily, but that is technically speaking why that one wasn't looking so happy. So now let's divide by g over 11 on both sides. So 0 equals g over 11 minus 2s. 2s equals g over 11. And we'll get it just in the bottom here. I'll move over here. Therefore, s equals g over 22. And that, we'll punch that into our calculator. Is 0.45 meters, which makes sense. It's going to go up there a little bit further, stop, and start going down. There there we have it.